So we saw that the optimization problem that we intend to solve is to find the optimal W which minimizes, this is what we saw in the previous video, right? Which minimizes given n points, it minimizes log of 1 plus exp of minus yi w transpose xi, right? This is a problem that we're trying to solve, right? Now imagine we get the optimal W star. This optimal W star is called the weight vector. It is called the weight vector. So remember the W that we have, if you have to do W transpose xi, right? Your W, we should always remember, I'll stop writing the star from now onwards. Whenever I say weight vector, I'll just write it as W. It means the optimal W star, okay? Just notation wise. I don't want to keep writing the W star from now on. Whenever I write a W and say weight vector, it means the best W star. Okay, so the best W or W star, right? So now given our weight vector, this is important here. Given our weight vector is also a d-dimensional vector if you think about it, right? So if each of my points xi, right, your weight vector also belongs to Rd, because each of my points also belongs to Rd, right? Otherwise we can't perform this multiplication. I can't do W transpose xi if they're not the same dimension, right? The first thing that you have to note is the weight vector is a d-dimensional data point. Okay, this is the linear algebraic interpretation. Of course, the geometric interpretation is very simple. If this is my separating hyperplane pi, right, my W is normal to it, and all of my negative points are here, right? And all of my positive points are on this side, right? Right? That's the geometric interpretation. I completely agree. But remember, the W is a d-dimensional vector. We should not forget that, right? Now, what is the interpretation of W? Let's try to understand W in more detail, right? So remember, each of your data points is a d-dimensional data point, which means there are d features, right? That's what it means. We use the word feature and dimension interchangeably, right? So if I have d features, so my weight vector right now is W1, W2, W3, so on and so forth, WD. And I have D features. I have feature 1, feature 2, feature 3, so on, D features. So corresponding to every feature, I have a weight associated with it. Right? That's how that's one way to understand the weight vector. I'll repeat the statement. For every feature, I have a weight associated with that feature. That's why it's called a weight vector. Now, as you might already understand, the decision. So let's assume given a new query point. Let's assume I'm given a new query point, and for this query point, I want to estimate what is its class, YQ. Right? How do I do it in logistic regression? The rule is very simple. If W transpose XQ is greater than 0, then YQ equals to positive. It's a positive class, right? Similarly, if W transpose XQ is less than 0, then your YQ is negative class. And this comes from simple geometry, right? This comes from simple geometry. Suppose if my query point was here, if I multiply this point with W, since it is on this side, remember my separating hyperplane, my decision surface in logistic regression is this plane. Everything on this side of the plane is positive. Everything on this side of the plane is negative. The plane itself is unknown. If a point lies on the plane, we would say it's neither positive nor negative, right? But if a query point lies here, which means suppose if this was my XQ, then W transpose XQ will be positive, and hence we are calling it a positive point, and similarly for negative points, right? This is my decision surface. This is my decision. Given a query point, this is how I determine its class label. We also saw the probabilistic interpretation, right? So we also saw the probabilistic interpretation when we learned about the sigmoid function, right? So the probabilistic interpretation is the sigma function of W transpose XQ is equal to the probability that my YQ is positive class. We saw this when we learned about the need for the sigmoid function, right? So this is a probabilistic interpretation. This is the simple decision. If you want to decide plus or minus, this is what you would do. If you want to get a probability value of what is a probability that YQ equals to +1, instead of just taking this value, you apply this sigmoid function that gives you a probability value, because sigmoid function gives you values between 0 to 1, right? We saw this probabilistic interpretation earlier. Now let's understand the interpretation let's dive into the interpretation of W a little more into detail, right? So first let's just say, right, because we have a weight vector, which is d-dimensional, right? So let's assume I have a dimension fi, feature I. Corresponding to it, I have a weight vector, I have a weight value which is wi, right? Now imagine if wi is positive. Remember that this wi corresponds to feature I. Okay, if the weight corresponding to feature I is positive, then what happens? Let's work out the details, right? If this is positive, then what happens if I have a query point xq? Because wi, right, the ith component of w will get multiplied by the ith component of xq, right? So if xqi increases, what happens? If xqi increases, what happens then? If xqi increases and if wi is positive, okay, since wi is positive, my wi xqi also increases, right? It's because my wi is positive, right? So if my wi xqi is increasing, as xqi is increasing, so what does this imply? Because what is my decision surface? My decision surface is W transpose xq. And what is W transpose xq? It is basically summation of I to 1 to d wi xqi. This is what it is, right? This is a vector notation. This is a scalar notation, right? So now what does this mean? This means W summation I equals to 1 to I wi xqi. This whole thing also increases. If this whole thing increases, remember, if this whole thing increases, then what does this imply? The sigma of this whole thing, the sigma of W transpose xq also increases, because we saw that sigmoid is a monotonically increasing function. If the sigma increases, what does this mean? The probability that yq equals to +1 also increases, right? This is case 1. Let me write it as case 1. So what is case 1? Case 1 is, if my weight vector wi corresponding to feature I is positive, then if for a given query point, if the ith component or the ith feature value increases, then the probability that yq equals to +1 also increases. That's what I tried to come to, if wi is positive. Now case 2, we should also remember case 2 here. What is case 2? Case 2 is, what if wi is a negative value? What if wi is a negative value? Then if this is the case, then as xqi increases, what happens? wi xqi will decrease, because this is a negative value, right? This whole thing will decrease. If this is decreasing, then summation of wi xqi, I going from 1 to d, this whole thing also decreases. If this decreases, then sigma of W transpose xq also decreases, which means the probability of yq equals to +1 decreases, which implies probability of yq equals to -1 increases. Because remember, we should always remember this, probability of yq equals to +1, right, is equal to 1 minus probability of yq equals to -1. Because given a query point, it can either be positive class or negative class, right? So here is the interesting conclusion. If wi is positive, then for a given query point corresponding to feature I, this is also corresponding to feature I. If the ith feature increases, its probability that it belongs to positive class increases, right? Similarly, if a weight corresponding to feature I, is negative, then given a query point, if its ith feature increases, its probability of its negative class increases. Not positive class, negative class, right? So this is very, very important interpretation of the weight vector. I'll repeat it just for clarity. Okay, given a feature I, if the weight vector's component corresponding to feature I, or if the weight corresponding to feature I is positive, then for any query point xq, if the feature value corresponding to the ith feature increases, if the value corresponding to the ith feature increases, its probability of it belonging to positive class increases. Remember, this is positive and this is positive here, right? Similarly, in this case, here it is negative, here it is negative. So if your weight vector is negative as the ith feature for a given query point increases, its probability of it becoming negative, the probability of its class label being negative also increases. This is a very, very important interpretation of weight vector W.